Swayam Prabha. Digital India. Educated India.
Very important parameter, fuel consumption, specific fuel consumption. Very, very important because everybody is interested in having a car which is very efficient. So it's nothing but the ratio of fuel consumed per hour to the power output that the car is delivering. This is again two specific fuel consumption definitions. One is called indicated specific fuel consumption and the other parameter is called brake specific fuel consumption. Brake specific fuel consumption is extremely important. More important than indicated specific fuel consumption. How do we define it? So as it is written, specific fuel consumption is ratio of the fuel consumed per hour to the power output that is delivered. Okay. So, so the specific fuel consumption, brake specific fuel consumption will be fuel used in kilograms per hour divided by brake power produced in kilowatt. Okay. So this is mf dot and this is brake power and the units will be kilograms per kilowatt hour. That's the unit. You can put it grams per kilowatt hour or kilograms per kilowatt hour. Okay. Very efficient diesel engines consume about 220, 230 grams per kilowatt hour. Efficient ones. And of course, inefficient ones can be 300, 350. Okay. Similarly, if you have indicated specific fuel consumption, this is defined as the same except the fuel power, the power term, fuel used in kilogram per hour divided by indicated power again in kilowatt, and this is defined as mf dot, mass of the fuel consumed per hour divided by indicated power again in kilogram per kilowatt hour. Which will be lower and which will be higher? Brake specific fuel consumption will be higher in this case. Okay. Heat balance. What is heat balance? Heat balance is balance sheet. What is balance sheet? Balance sheet, all of us know. Balance sheet of any business entity is where the money is coming from and where the money is going to. You have to match both of them. Expenditure and income has to be matched. That's called balance sheet. Similarly, in the engine parlance, if you are making a balance sheet, heat balance sheet, so this is not money balance sheet, this is heat balance sheet. So how much heat is coming in, how much energy is coming in and where it is going. So if you look at the energy, where it is coming from, the only source of energy in an engine is fuel, combustion of fuel. And where it is going? It is going first and the foremost is useful power production, because ultimately that's what you want. And what are the other sources? It is going into coolant, because engine requires coolant in order to keep its temperature under control. So there is some heat that is being lost to coolant. Radiator is there that is finally losing the heat to the air. If you look at the exhaust, a significant amount of heat goes into exhaust, because exhaust is hot, exhaust gas is hot. So that also takes away a lot of heat. And then we already studied that there is a lot of heat that is going in the friction, right? And then there are a lot of unaccounted losses. What are these unaccounted losses? For example, you club all other losses into unaccounted losses. For example, when you run the engine is hot, right? So it's doing the radiative heat exchange, right? So it has significant amount of energy, maybe 2, 3, 4%, but it's very difficult to estimate it, right? There may be some amount of fuel that is passing through the rings into the chamber, and which goes into the atmosphere through some holes in the engine, right? This is crankcase blow by emissions, and then you have a dip rod. That's not where you check the level in the engine, level of the oil in the engine. It's not completely sealed. So the fuel air mixture through those rings passes into the bottom chamber, and from the dipstick hole it goes into the atmosphere. It has some fuel in it. You can't estimate it. So what you do is you account everything that you cannot account for very accurately and call that as friction and unaccounted losses, and that's about 10 to 15% of the total thing. So there is a brake power output, there is a coolant loss, there is heat going to exhaust, there is friction and accounted losses, radiation losses, everything put together. So these are the 4 main headings where the fuel energy is actually used in an engine. Okay. If you look at exhaust parameters, there are 2 types of emissions that are coming out. One is the solid phase emissions, the other one is gaseous phase emissions. Gaseous phase emissions will include what? It will include carbon dioxide, it will include hydrocarbons, it will include carbon monoxide, it will include oxides of nitrogen, it may include oxides of sulfur if sulfur is present in the fuel. These are all gas phase emissions. And there are solid phase emissions. What are those solid phase emissions? These are particulates that come out. Of course, they are a part of the smoke that comes out. Okay. So smoke, if you collect it on filter paper, you will be able to see some solid particles. Otherwise, if you don't collect them, they just look very visual nuisance in the form of smoke. So smoke and other discharge gases constitute the exhaust emissions. Smoke is an indication of incomplete combustion because it is taking away a lot of carbon, right? So it is not only a nuisance, it is also a fuel that is going out, right? Some part of the fuel energy it takes away. So it has become therefore necessary to view them as performance parameter after the enforcement of the stringent emission norms. And some of the emission norms that are applicable worldwide, there are different norms. For example, Europe, the emission norms are Euro norms, Euro 1, 2, 3, 4, 5, 6. Now they are 5, they are going into 6. Okay. And for example, in US EPA norms, US Environmental Protection Agency, that's the central agency that makes the norms. It's called US EPA norm. US EPA 1, 2, 3, tier 1, tier 3, tier 4. Similarly, there are different norms in India. These are called Bharat Stage 1, Bharat Stage 2, Bharat Stage 3, Bharat Stage 4. Now we are directly jumping from Bharat Stage 4 to Bharat Stage 6, right? Come April 2020, right? So that's where we are going. So Bharat Stage norms are pretty much copy of Euro norms with some modification, with some adaptation to Indian driving conditions. So they have become extremely important, and that's why control of the emissions has also been treated as a performance parameter. Specific weight, very important parameter. It is defined as the weight of the engine in kilograms for each brake power produced. That means how many kilograms of engine weight will produce 1 bhp or 1 kilowatt power. So that's the specific weight. And as I told you earlier, if you are looking at an application like aircraft, you would like to have very little specific weight compared to ground transportation engine. And if it is just a stationary application like a generator, you don't even care about specific weight. I mean, this is just standing, even in car you care about specific weight to some extent, but not to the extent that you care about in aircraft. But for generator, you don't really care too much about the specific weight. So a specific weight plays an important role for applications such as aircrafts, helicopters, and things like that. Okay, so these are the performance parameters. Now question is, if you want to evaluate the performance of a particular engine that you have or you have developed, what measurements should you take in order to measure these performance parameters? So there are certain measurements, certain sensors that have to be put in the engine. What are the measurements? So first basic measurement that you have to do is speed. Second basic measurement is what's the fuel consumption, right? Third basic measurement is what is the air consumption. Fourth basic measurement, what is the smoke opacity or smoke density. Fifth measurement is what is the power produced by the engine. Sixth measurement is what is the indicated horsepower and frictional horsepower. Then you would like to find out what is the cooling heat going into the cooling water. You would like to find out how much is the heat going into the exhaust, how much is the different types of pollutant species being emitted by the engine. So these are some of the basic measurements. There are more measurements than this, but this is just the basic, and we'll just restrict our discussion today to understand this, and then later in the course we will go to more advanced measurements. Okay. So one of the basic measurements of speed, how you can measure. This is very simple. You have a mechanical tachometer. What does a mechanical tachometer do? You have a shaft and there is a rubber coupling, and you just insert in the center of the shaft that you want to measure. It will rotate with the same speed as the base shaft, and it will tell you what is the speed. But that's a very crude way. Okay, you may even injure yourself if you go very close to the shaft, and that's not the way the experiment should be done. So this is one of the initial ways to use mechanical tachometer. Now there are many other ways. For example, this is the engine, this is dyno, and this is the shaft. You can have a single tooth, okay, and you can have a magnetic pickup. So when the tooth passes in front of the magnetic pickup, so in one cycle that magnetic pickup will give you one peak, okay, and that you somehow capture, and you can then put it in some kind of acquisition system to actually tell you how many times it is going in front of that single tooth, how many times that tooth is coming in front of the pickup, and you can figure out what is the RPM. Okay. Then there are more advanced sensors. For example, one of the very simple devices is that on the flywheel you can have a reflective tape, okay, and then you can have a sensor which emits some kind of a radiation, and then there are other sensors, when it is reflected back it captures them. So in one rotation, whenever the tape comes in front, the radiations are pick up, and so Hall effect sensor is something similar. So this is the way you actually capture the speed. Okay. Then how do you measure the fuel consumption? Second measurement is fuel consumption. So fuel consumption is measured in two different ways. One is the gravimetric method, the other one is volumetric method. What is gravimetric method? Gravimetric method means you are measuring the mass of the fuel consumed, and volumetric method means you are measuring the volume. So once you are, how you can measure the volume consumption is very simple. You put a burette, okay, you have a certain sensor at certain location, after certain volume you have another sensor, and you just take a stopwatch, measure this. So this is gravimetric, this is volumetric method, very simple method. You will know that okay, my 20 ml is consumed in 30 seconds, and you can just do simple calculation to figure out what is your volume consumption rate per hour or per minute or per second, whatever you want to do, you can do the calculation. Okay. But this is not very accurate. Why it is not very accurate? Because suppose I am doing a measurement at 45 degree centigrade ambient temperature. My fuel is at 45 degree centigrade, so it will have a different density. So different amount of energy is going in. Another day I do a test at 15 degree centigrade ambient temperature. So then what will happen? Will I have the same volumetric consumption? The answer is no, because now my fuel density has increased. Temperature reduces, my density increases. So now I have lesser volumetric energy consumption, volumetric fuel consumption. So this is therefore not very accurate. What is more accurate is I am interested in finding out what is the mass consumed, because please remember, when we say heating value, what is the unit of the heating value? It's gram per kilowatt hour. It's gram, not milliliter. So even there it is gram. So certain mass has certain energy. Certain volume does not have a fixed energy. Volume energy content of a particular volume of fuel will change depending on the ambient temperature. But volume, the energy content of 1 gram of fuel will not depend on the temperature. 45 degree it will have the same value, 15 degree also it will have the same value. So measurement of the mass is what is more reliable. So volumetric, gravimetric is volume of the fuel consumed multiplied by the specific gravity is it can be used, or you can directly measure the mass of the fuel consumed, and that is what is more accurate. Okay, if you are doing the volumetric fuel consumption, and if you want to actually do a correct measurement, then it is a good idea that you also record the temperature, and you also record the density of the fuel at that temperature. If you use this data, then you will know, you can convert your volumetric fuel consumption into gravimetric fuel consumption very, very accurately. Is that clear? Third is the measurement of air consumption. So again, air consumption, air consumption, there are two methods. One is the air box method, the other one is air flow meter. Now in the air box method, see, you have to understand that measurement of airflow in an engine is extremely difficult. Why it is extremely difficult? Because air is only taken in during one stroke. In remaining 3 strokes, it's not taken. So the air intake is fluctuating in nature. So if you want to measure for any flow of fluid, there are 2 devices, orifice plate and venturimeter, right? You must have studied in second year. But they cannot be really directly applied because it's fluctuating. And if you apply these devices, the manometer will keep fluctuating and you will never know what is the correct reading. So what you do is, you take a drum or an air box, which is say 400 to 500 times higher volume compared to engine swept volume. And then there what you do is, on one side you put a rubber diaphragm, so that rubber diaphragm can go in and out without much of a problem, okay? And you connect that to the engine. So engine will have pulsations. Those pulsations will come in the tank, and you will have a diaphragm. And this box, in there, what you can do is you can put an orifice at the entry of the box. So the volume is so large that these fluctuations actually do not travel all the way to the orifice. So there, if the orifice plate, across the orifice plate, if you put a manometer, you will be able to do correct measurement, because there the manometer will not fluctuate. This is the air box meter. So using a measuring orifice in conjunction with a smoothing capacity in a air box is very simple and easy to construct, very, very cheap method. The other one is air flow meter, or this is also called laminar flow element. So what you do is, you make the flow laminar, and then this measures the mass of the air flowing through a tube, but it is very, very expensive, okay? So air flow meter or laminar flow element, this is more correct method to measure, but this is expensive as well. If you look at the exhaust smoke, there are 3 basic methods: Bosch measurement of the smoke, Hartridge method, and PHS method. So they give you soot density in terms of grams per meter, grams of soot per meter cube of exhaust gas. Okay, I will discuss in detail when we discuss the instruments. At that time, I'll discuss these methods in great detail. The next method is measurement of brake power, how much power the engine is producing. So brake power, this requires the measurement of torque and angular speed, because if you want to measure the power output, the simple formula for the power output is P equal to 2 pi NT. Right. What is N? N is the rotational speed of the engine, or angular speed, whatever you may like to say, and T is nothing but the torque. So if you know the angular speed or the speed of the shaft, and if you know what is the torque being produced, you will be able to calculate the brake power. So dynamometer is a torque measuring device, and there are 2 types of dynamometer. One is called power absorption dynamometer, the other one is called power transmission dynamometer. Power transmission dynamometers are not really used in the engines. These are mostly the power absorption dynamometers. So if you look at the working principle, there are many types of dynamometers. So for example, one of the very simple brake dynamometer, this was also called rope brake dynamometer. Brake dynamometer is that you have a shaft and a drum which is rotating, and there is a stator, okay, and there is a coupling force, and then there is a scale, and this is hooked at this. There is a counterbalance. So the shaft is rotating, and some force is being exerted by the stator, which is measured here, okay, and this length of the arm of this where you are measuring the force, this is the force and this is the length of the arm. So the work done per revolution is 2 pi Rf, and the external torque is S, which is the force being measured into the length, okay, and moment balance is S into L equal to R into F. So basically you can calculate the P equal to 2 pi NT here. There are absorption dynamometers. So absorption dynamometer, they basically absorb the power output of the engine with which they are coupled. Power absorbed is usually dissipated as heat, okay. So for example, it could be a Prony brake dynamometer, which is not used, it's just these are historical dynamometers. It could be rope brake dynamometer, or hydraulic dynamometer. So nowadays the hydraulic dynamometers are very sparingly used, but what is used mostly is eddy current dynamometers and transient dynamometer, AC and dynamometer, DC dynamometer. Transient dynamometer is also known as AC dyno. So either you have AC dyno or transient dyno, or you can have DC dyno, or you can have eddy current dyno. I will just show you some of these things. So basically in Prony Bragg you have these two blocks, the shaft is rotating here, this is the torque arm, and here you put the weight balance, okay, and then as I explained, you can calculate what is the brake power being generated. Similarly, in a rope brake, this is one of the very historical dynamometer, very frequently used in 1950s and 60s. Very cheap, you have a rotating drum, you have a rope which is roped, you can see 2 layers of rope on this drum, and then there is a weight here. So this weight is acting, and there is a spring balance, and this is the rope are creating friction on the drum, okay. So they are trying to resist the motion, okay, and the balance of this force will be calculated by the spring. So here the brake power is calculated by pi d and W minus S. W is the weight and S is the force being shown in the balance, okay. And then you see, because of the friction, this will get heated up, okay. So this needs to be cooled, otherwise the ropes will burn. So there is a cooling water going on. So this is also no longer used, it's only of historical importance. The hydraulic dynamometer, again here you see there is a stator, this sky blue thing is a stator, and this red thing is rotor. So rotor is connected to the shaft, and when this rotates, water is coming in. So water will have some kind of eddies being developed, because this is the stator and this is moving, and because of this there will be the power that is generated by the shaft will be dissipated into the friction, into the turbulence that is created in the water, and that's how basically the power is dissipated. And here you have the torque meter to see how much torque is being generated. So this basically, this hydraulic dynamometer works on the dissipation of power through the fluid friction, and this is a cheaper dynamometer used in some laboratories, but it's not very highly accurate, okay. So in our lab we don't have any hydraulic dynamometer because of the issues that are encountered. What we have is this eddy current dynamometer. So eddy current dynamometer, again this is the engine shaft, and in eddy current dynamometer this is a rotor. So the rotor rotates, okay, and here you have a coil. So coil basically does the magnetization. So when it creates magnet, you see there are small circuits of eddy currents that are generated, okay. So this eddies actually try to resist the motion of the rotor, okay, and then they get heated up, everything gets heated up. So you have flow of water here, flow of water, which takes away the heat that is being generated. So the working principle, so basically construction is, stator is mounted on by a number of electromagnets, you have number of electromagnets, a rotor disc made of copper coupled to the output of the shaft, so it is coupled, okay. The working principle is, rotor rotation induces eddy current in the stator due to change in the magnetic flux that is set, okay. Eddy currents are dissipated to produce heat, so a lot of heat is produced in this zone, and then the torque is measured by the moment arm, just like any other dynamometer, and then this load is controlled by regulation in the electromagnet. So if you increase the current here in the electromagnets, more eddies will be generated, and therefore you will be able to absorb more power that is being produced by the engine, right. So you basically regulate the current that is going in the coils. So load is measured by load cell after the calibration, and this is how the dynamometer works. This is the transmission dynamometer. You can see, basically transmission dynamometers are also called torque meter. The energy or power produced by the engine is transmitted through the dynamometer to some other machines where the power developed is suitably measured. There are many kinds of dynamometers, for example belt transmission dynamometer, epicyclic train dynamometer, and torsional dynamometer, but they are not very important for engine applications, okay. The next thing that is important is measurement of friction. So measurement of brake power we can do, measurement of indicated power is slightly difficult. So if you can calculate the frictional power, then you can just add brake power and frictional power and find out what is the indicated power, okay. So with that angle, suppose you have a multi-cylinder engine, how do you measure the frictional power? So frictional losses are dissipated as frictional heat to cooling system. So lower friction means more brake power and lower brake specific fuel consumption, and that's what we want. So I think ultimately at the end of the day, we want to design an engine which has lower friction so that we can get higher power output, more power will be available at the shaft end, and you will have lower fuel consumption per unit power produced, right? So that's what we want. So level of friction decides the maximum output of the engine, and there are three ways in which the engine you can use for basically determine the frictional horsepower. What are these three tests? One is called Whelan's line test. The second test is called Morse test, and the third test is called motoring test. These are the three tests that I will introduce to you today. So the first test is Whelan's line test or fuel rate extrapolation. So please understand, what you do is you make a curve where you have brake power on the x-axis and you have fuel consumption on the y-axis. Okay? So what you do is you actually start the engine. So engine will be here, 0. Engine will not produce, it's just idling. It will produce some power. It will have some specific fuel consumption. Then you start producing power, 5 kilowatt, 10 kilowatt, 20 kilowatt, and so on, and then you keep on getting points. Okay? And then when you come to the rated load, this can be 1 to 25 for a 25 kilowatt, this can be 1 to 5 for a 5 kilowatt, or smaller engine will have smaller x-axis. So that you can figure out. So you will see that this is almost a linear curve to some extent, and when you start extracting more and more power, the specific fuel consumption start going up. So it will start going up. Okay? So when you do the experiment, you can have 1 point here, 1 point here, and few points here. So you make this curve. So what you do is, in the linear portion you join, and then you extend it to meet the x-axis. So this will be your frictional power. What does it mean? You have a linear curve, okay, and when you extend it, that means here when you are not producing any power, you are having this fuel consumption. Frictional power means you will have 0 fuel consumption, and so that means when you start the engine and you come up to this level, all this fuel is just wasted in overcoming the friction, and that is why this is called frictional power. So this is Whelan's line test. Okay? So basically, to summarize it, you have gross fuel consumption versus brake power at a constant speed is plotted, and the graph is extrapolated back to 0 fuel consumption. Okay? Negative intercept on the brake power axis is called the frictional power, and this is applicable to CI engines, only applicable to CI engines. Okay? This is not applicable to SI engines. Light curvature at light loads, this is light curvature, there is a slight curvature. This is due to difficulty in injecting accurately and consistently very small quantity of the fuel per cycle. Okay? The problem with this is that suppose you have, this is ideal situation where all the points will be linear, but in real practice one will be here, one will be here, one will be here, and if you decide to join these 2 points, you may end up here. So the error in your frictional horsepower estimation can be really large depending on which points you try to join, and any experiment you do, there is always some experimental error. So this is one of the drawbacks, that graph here is not exactly linear, and it may give some error while you are doing extrapolation. So one has to do it extra carefully, and one has to repeat the test 2 or 3 times in order to get a fair estimate, and still you will have some errors in your extrapolation. Yeah. Friction power at a speed remains constant, yes, because the engine is rotating at the same speed. So that's why you see this is here it is said that at constant speed. So frictional power will change with the speed. So if you are having low speed, obviously the friction will be lower, and if you are having high speed, the frictional horsepower will be higher in this case. So frictional horsepower will vary with the speed. It may not vary so much with the load. Okay? The second test, which is mostly applicable to spark ignition engine, it's called Morse test. It's applicable only to multi-cylinder engine. This test is applicable to both single cylinder as well as multi-cylinder, but Morse test is only applicable to multi-cylinder engine, particularly the SI engines. So engine is first run to required speed and the output is measured. So what you are doing, if you have a 4-cylinder engine, you will run it to a certain speed, you will maintain that speed, and then what you will do is you will pull the spark plug from the spark plug, not the exact spark plug, but the supply to the spark plug, you will stop. So that means in a 4-cylinder engine, now what is happening? Only 3 cylinders are providing power, but the friction is going to all 4, right? So one cylinder is cut out by short circuiting the spark plug or by disconnecting the injector. You can also disconnecting the injector. I said this is for diesel engine, but most test is not so much preferred test for diesel engine. You can do it if you want, but this is, you see, pulling the injector out or stopping the supply to injector is not that easy. That's why I said it is not so much preferred test for CI engine. But if you want, you can do it. Theoretically, you can do it, but practically it is not really so much popular for CI engines. All other cylinders motor this cutout cylinder, because now the power is being produced by 3 and consumed by 4, and output is measured by keeping the speed constant to its original value. Okay, so speed you maintain, and the difference in the output is a measure of indicated horsepower of these cutout cylinders. So what you will do is you will do it for the first cylinder, then you will do it for the second cylinder, then you will do it for the third cylinder, you will do it for the fourth cylinder, and then that way you can have the frictional horsepower as well as the indicated power for all 4 cylinders. So this is the Morse test. The third test is motoring test. So in the motoring test, it's very simple. The engine is first run to desired speed on its own power, and constant speed load conditions are maintained for some time, and oil, water, engine component temperature reach a stable condition. So you run it for 10-15 minutes, everything stabilizes, and power of engine during the period is absorbed by swinging field type electric dynamometer. So whatever power is being generated, you have a swinging field dynamometer attached to it, and then what you do, you cut off the fuel supply, and when you cut off the fuel supply, the engine stops. Engine practically stop firing, but then this is a swinging field dynamometer, you start providing the current to it. So when you start providing current to the dynamometer, it start acting as a motor, and it start rotating the engine. So now the engine is running at the same speed, not producing power, but the power is being generated by the dynamometer, and dynamometer generally is acting as a motor, and motors have very high efficiency of 98-99%. Okay, so fuel supply is cut off and dynamometer is converted to run as a motor to drive the engine at the same speed as the previous one, and everything else is hot, right? So everything else is stabilized condition. So power supply to the motor therefore is a measure of frictional horsepower, because whatever power you are supplying is going to get converted into shaft power, because motor is a very efficient device, and that power is going to run the engine, and what it's doing is overcoming only the friction, because it is not producing any useful power, right? So this is how you do the motoring test. So during the motoring test, water supply is also cut off, because if the water keeps on going into the engine, it will lower the temperature. So you cut off the power supply so that the temperatures are maintained at the realistic levels. Okay, so this is the third way in which the frictional horsepower can be measured. Difference between the indicated power and brake power. Method of finding the frictional power by computing difference between the IP and BP is the ideal method. Due to difficulty in obtaining actual indicator diagram, this method is usually only used in research laboratories. Indicated power, if you want to calculate the indicated power, you have to put the pressure transducer in the cylinder, and you have to measure something called pressure crank angle history. That means in one cycle how the pressure is changing. Okay, this is called P theta diagram. I will explain that to you in the later lectures. So using this you can figure out what is the indicated power, but it can only be done in the very well equipped laboratories. If your laboratory is not very well equipped, then the best way for you is that you measure the friction power, and you know the brake power, it's very easy to measure, add them, and then you find out what is the indicated power. But if you have a well equipped lab, then you can directly measure the indicated power, you measure the brake power, and then you, by subtraction, you find out what is the friction power. Okay, so which route you take, it depends on what is the level of sophistication that you have in your laboratory. Okay, so there are two methods of finding the indicated power of the engine. First is the indicator diagram with the help of suitable engine indicator. So, engine indicator is nothing but a device which is used, it is a mechanical device actually, is not routinely used now, but in good old days it was a device which was used. So, you used to put a paper and a pen, and this is connected through some mechanism, and then it used to plot the PV diagram. Okay. So, that was one way to look at what is the indicator diagram. But when I started studies of the engine in 95 or so, it was already obsolete by that time. Okay. So, the other one is that measuring the BP and FP and adding the two. So, instead of indicator diagram using the indicating mechanism, now you use pressure transducer and data acquisition system. So, first indicator diagram can be drawn by plot of variation of pressure in the cylinder over a full or part load. It is an indication of the process of converting heat into mechanical work. So, it can be either plotted by PV diagram, as I said, using the indicator mechanism, or nowadays this is calculated by using pressure crank angle diagram by drawing the P theta diagram. Pressure on one axis, one vertical axis, and theta crank angle on the x axis. So, engine indicating device, modern engine indicating device has pressure sensing device, which is nothing but a piezoelectric pressure transducer. Okay. The second is the device for sensing the piston displacement or angular position, and the third is the display device for indicating pressure and piston displacement. Basically, this is pressure transducer, and this is the shaft encoder, which tells you where the piston is in the stroke. Okay. And this is the data acquisition system and computer. And then you have indicators such as piston indicator, balance diaphragm type indicator, electronic indicator. These are basically for PV diagram, the old version. Coming to the performance, as I said, heat balance sheet. If you look at the heat balance sheet, this is how a heat balance sheet of a typical engine looks like. So, what you do on the x-axis, you plot the speed. On the y-axis, you have energy in terms of percentage. So, you plot from 0% to 100%. Okay. So, first you want to figure out, so this is for petrol engine at full throttle, that means full throttle you have put, speed is limited to 1000. So, some amount of energy will be converted to useful work. So, suppose 20%, and then some amount of energy is going into coolant. How do you figure out the coolant? You measure what is the coolant in temperature, you measure the coolant what is the output temperature, and you measure what is the mass flow rate of the coolant. So, MCP delta T, very simple. Similarly, for the exhaust losses, you figure out what is the mass flow rate of the air that is going in, what is the fuel flow rate. So, mass flow rate of air plus mass flow rate of the fuel will be the mass flow rate of the exhaust. What is the CP of the exhaust, and what is the intake air temperature, what is the exhaust gas temperature. So, you can figure out what is the exhaust heat losses, and remaining thing you just do not worry, because everything else is radiation and other losses, unaccounted losses. So, basically you will calculate what is the useful work from the brake power output that you are getting. You will calculate what is the coolant loss, you will plot what is the exhaust loss. Say for example, at 1000 RPM you put these points, at 2000 RPM, 1500 RPM you put all these points and then connect them. So, this will be the envelope for useful work, this will be the envelope for coolant, this will be the envelope for exhaust gas, this will be the radiation loss, right. And if you look at this diagram, one of the things is very clear that initially, if you look at the entire speed spectrum, at certain speed you get higher thermal efficiency, but if your speed is lower or higher than that, then the thermal efficiency goes down. Okay, then energy that is going into the power production actually goes down. And also these numbers are typical, you see 20, 25, 30%. So, typically the SI engines will have generally lower efficiency, because thermodynamically they are at lower compression ratio. So, their thermodynamic efficiency is anyway lower than diesel engines. Coolant, you can see this is more or less same, but if you look at the exhaust gas, the more at higher speeds, when you are putting more amount of fuel, lot of energy goes into the exhaust gas. That is why now they are talking about regenerating some of the energy from the exhaust gas. So, Peltier effect they are trying to use and generate some electricity from the hot gas that is going out from the SI engines. So, this is one big research area nowadays, how to capture the exhaust gas energy, because here you can see that more than twice of the useful work energy is going into exhaust. And then you see this is radiation. So, here what you notice is that at low speeds you have a lot of losses, because here at low speeds the friction will be high because you will be running the engine at lower temperature. So oil viscosity etc. is high, and therefore the friction is high. And as you keep on increasing the speed, this friction and encountered losses actually reduce. So let's summarize this. So in summary, the engine performance is usually studied by heat balance sheet, which include heat equivalent of the brake power, and then heat rejected by cooling medium such as coolant and exhaust gas. Okay, then you have unaccounted losses from different components, and the percentage of heat rejected to coolant is more at lower speed. About 35% is going into coolant, and it reduces at higher speed, so about 25%. And considerably more heat is carried out by exhaust at higher speeds. So this is the story as far as the petrol engines or spark ignition engines are concerned. So if you look at the typical components of heat balance at full load, so SI engine typically 21 to 28% brake thermal efficiency. If you look at the same numbers at CI, much better, 29 to 42% energy will go into useful work, and heat rejected by cooling can be 12 to 27%. Here this will be 15 to 35%. But if you look at exhaust gas temperature, this will be much higher here, up to 55%. And exhaust gas from the diesel engine will be lower. I will just tell you one simple example. Just do this experiment. If you have a bike, run that engine at full speed, full load, pull the whole throttle for half an hour. You will see that the exhaust pipe will become red hot. Okay, so because the temperature of the exhaust can be as high as 700, 800, 850 is possible. That's why the exhaust pipe can at some point start glowing. But this will never happen in a diesel engine. Diesel engine maximum temperature that you can attain is 600, 650. That's also very unlikely. So the point that I am trying to make is that the exhaust heat loss from diesel engine as a percentage of the total energy that you are putting in is actually lower in CI engines compared to SI engines. Okay, then there are unaccounted losses, and this could be very high in SI engines because in gasoline engines we are having homogeneous combustion. So if it is incomplete, lot of fuel will go without burning. I showed you yesterday, in last class, the two-stroke engine. Lot of fuel goes out without burning. So that also contributes to unaccounted losses. Whereas no such loss is there in CI engine. Most of the combustion efficiency of a diesel engine is as high as 98%. That means whatever fuel you are putting in, 98% of that will get converted to heat. Okay, the best combustion efficiency for a SI engine is 95%, best. And the worst combustion efficiency for a diesel engine is typically, worst one is 98. So you can imagine, there is a lot of difference in combustion efficiency of the SI and CI engines. Okay, this is the heat balance sheet of a diesel engine, of a petrol engine at different vehicle speeds. So what I showed you earlier was engine speed, here it is vehicle speed. So you can see this vehicle speed in 0 to 80 km per hour. At 0 speed, of course, you are not doing any useful work, and so this is the useful work. And then you have some accessories, so a lot of energy goes into accessories. Then pumping work. What is pumping work? Pumping work is the amount of energy that you spend in pushing the gases out and sucking the gases in the exhaust stroke and intake stroke. So you can see it is very high in the beginning and it reduces. Then this is the friction, engine friction. Okay, so basically friction and unaccounted losses are this envelope. So they have brought from the top, they have brought it to the bottom. So you can bring them up and down. This one is the cooling loss, this one is the exhaust loss. Okay, so this is as far as the vehicle is concerned. So the shape of the curve will be different when you do it for the engine, the shape of the curve will be different when you do it for a vehicle. So if you look at the performance of a SI engine, this is the efficiency is given here. Engine speed, again this is only on the engine. If you look at the brake thermal efficiency, this is the brake thermal efficiency curve. If you look at the indicated thermal efficiency at the piston, this is the indicated thermal efficiency curve. Brake thermal efficiency is maximum around here. So this is the specific fuel consumption. Scale is given here. This is the SFC. It is very high when the efficiency is poor, is SFC is minimum when the efficiency is highest, obviously, okay, because these are inverse. And this is the mechanical efficiency. Mechanical efficiency, you can see at low speeds it is high, okay, because the friction is low, and as you increase the speed you are having more friction. That many more times the piston has to travel against the liner, so you have drop in the mechanical efficiency. It can range from 90% to 70%, up to 75%. Okay, so at full throttle, the brake thermal efficiency at various speed can range from 20 to 27%, and you have maximum efficiency at mid speed. So this is the performance of a SI engine. So this is the horsepower here and the engine speed given here. This is the brake specific fuel consumption we have just discussed. This is the frictional horsepower. Okay, at low speeds, low friction, at high speeds, high friction. This is the brake mean effective pressure. This is the brake torque. This is the BHP. This is the IHP, indicated horsepower and brake horsepower. Okay. Similarly, this is that wide or full open throttle. I think it's similar, just the explanation. So this is the heat balance for a petrol engine. I think I have explained most of this. This is horsepower given here. This is the useful work, coolant, exhaust, radiation loss, etc. I'll skip this. I'll skip this as well. Now coming to CI engine, this is the brake horsepower given here. You see this is the useful work, this is the coolant loss, this is the exhaust loss. You can see that in the SI engine the exhaust loss was increasing with the speed, but in CI engine it does not increase so much. And then radiations increase in the CI engine. So total losses are lesser compared to SI engine, and coolant and radiation losses are more at low loads. If you look at this performance curve for 6-cylinder 4-stroke cycle automotive CI engine at constant speed, here the load is given in terms of percentage. You can see this is BMEP. So as the engine load increases, there is a linear relation between the load and BMEP. Okay. This is the BHP brake horsepower. This is the brake specific fuel consumption. One of the very important thing that you must notice is that the brake specific fuel consumption is minimum when you are operating at 85 to 90% load for a typical CI engine. This is correct for most of the CI engines. If you want the best fuel economy, you have to operate the engine at 85 to 90% of the rated load, maximum load. Okay, this is the exhaust gas temperature. As you increase the load, exhaust gas temperature goes up, also the torque goes up. So this is a typical performance characteristic curve of a 6-cylinder CI engine. So this also shows the same thing. This is brake specific fuel consumption. This is the BHP. As the speed increases, BHP increases. Torque output. I think I will stop here.